Hello and welcome to our second session today on the general stage. Thank you all for coming to PyData Global and taking your time to see some of these fantastic talks, these awesome speakers. Up next is Deep Learning in Energy Management, Non-Intrusive Load Monitoring for IoT Devices with Francesco Conti, who I will hand over to now.
Okay. Can I start? Yeah. Okay. I have to. Okay. Hi, everyone. Good afternoon, and thanks for joining this session. It's a real pleasure to be here today. Indeed, I'm glad about this opportunity to give a talk at PyData Global, and I hope you'll find this session about non-intrusive load monitoring, also known as NILM. I hope you'll find it informative. But let me start by telling you a little bit about myself. As you can see, my name is Francesco Conti, and I'm a telecommunications engineer. I'm specialized in data science, but actually I love signal processing and especially statistical signal processing. And I think that's why I started this career as a data scientist, and today I'm working on time series and so processing. Currently, I'm employed at Agile Lab. Agile Lab is a consulting company. We are based in Italy, but we do also have employees, but also customers in Europe and across the world. We work around data, in particular data engineering and good data practices. Our purpose is to elevate the data engineering game to a higher level, with the final goal of helping companies shape the future around good data practices, good data governance practices. But we work also in data science, and today I'm going to talk about this project that we implemented for one of our customers about NILM with the use of IoT devices and deep learning. So, an agenda, first I want to give you an overview about NILM. In few words, these techniques focus on understanding how much energy is consumed by each appliance in your house, in a house. And I want to give you more details about that and about also benefits of NILM. Then I want to discuss smart metering technologies and how they relate to IoT devices. And we'll focus on the specific case of Italy, which I think is quite advanced on this topic. I know it's strange, but we are advanced on this, and we implemented this Chain2 protocol that allows IoT devices to receive data from smart energy meters, and we will see how. Next, I want to give you an overview about state-of-the-art algorithms in this field. And finally, I want to share some thoughts about a deep learning paper architecture that we used in our work and some consideration about that. Indeed, in literature, you have papers working with high resolution data, but when you try to apply these to data from smart energy meters, especially in the Italian market, you have low resolution and irregular sampled data, so you have to deal with it. And we are going to see how. Okay, step by step. So non-intrusive load monitoring is a set of techniques used to disaggregate the total energy in a house into individual appliances. For example, look at this plot. You can see a signal. It represents the energy consumption. This could be your home. So you can see the energy consumption throughout the day. And I highlighted three regions. Here you have an oven, a dishwasher, and then a washing machine. And if you examine this plot, you can notice that these appliances have different characteristics in terms of frequencies, in terms of pattern of usage of the energy, on and off periods. So the final aim of NILM is to exploit these patterns in order to identify and quantify the energy consumption of each appliance. But we want to do this without installing separate sensor on every appliance. So as you can imagine, an ILM has a lot of challenges because we are dealing with data with a high variability. Indeed, if you think about a washing machine, you could have different brands for washing machines, but even if you consider your washing machine, it has different programs, different modes. Indeed, you can use a low temperature program or a higher temperature program, and this will change the pattern of the signal. And in NILM, we want to recognize these signals, and it is hard with this variability. Then we have to deal with noise, but also seasonality. Indeed, during summer, you use air conditioning, while during winter, you can use electrical boilers. And for this, we want to keep the most important challenge is that we want to keep costs as low as possible in order to match our business case. And this could be hard because we need to ingest data, to store data, to process data science, deep learning. So it could be very hard. And today I want to show you how these challenges can be overcome by the use of smart metering techniques with IoT devices and deep learning. Okay, but before let's discuss why should we be interested in this kind of technologies. So let's start with how an ILM techniques benefit and customers. Indeed, with this kind of technologies, users can have a clear picture of how much energy each appliance is using. And this is good because imagine providing users with a smartphone application, for example, to monitor their appliances. This kind of applications can spread awareness among people, helping them understand where the energy goes. And this will result in the second point, that is about saving and sustainability. Indeed, with this awareness, we can promote energy savings, so you can take smarter decisions, such as upgrading to better devices or just using an appliance less frequently. And this is good also for sustainability. Okay, shifting to energy supplier, we have benefits also for them. Indeed, they can increase the engagement of the final users with this kind of applications, and also implement gamification programs in order to give rewards to users. And the last point is about demand response. This kind of techniques consists in agreement among the energy supplier and the final customers, with the final goal of preventing the overload of the grid. And with demand response programs, users can have rewards from the energy supplier by shifting their energy usage in not critical hours. And in this case, we can use NILM to verify that a user is using intensive appliances just and only in agreed periods. So for example, a user must use car charging only in night hours to have rewards. Okay, now let's talk about smart meters. You can see a energy meter here. Indeed, in order to implement an ILM, we need data, and we need to collect data, and this data is typically gathered using this kind of meters, and they should be the data should be available at third-party services providers and energy suppliers in order to implement this kind of techniques. And in this, the European Union published the specifications for smart meters with the final goal of promoting energy efficiency in Europe. The main point of this specification is related to near real-time access to energy consumption data. Indeed, for this specification, a user and also third-party services chosen by the end user must be able to access the energy consumption in near real time. Italy is really pioneering in this field. Indeed, we introduced a first generation of smart meters even before the European specifications. And you can see this first generation introduced the chain one technology, and you can see this technology in the blue section of this diagram. And in this protocol, data is transmitted from the energy meter to the distribution company, and then it reaches centralized systems, and finally the energy supplier. But this path take at least 24 hours, so it's not suitable, as you can imagine, for near real-time applications. And for this reason, Italy adopted a second generation of smart meters that introduced the Chain 2 protocol. That you can see in green here in the picture, the new protocol. In this protocol, we have IoT devices. You can see a IoT device connected to an energy plug. This device will start to receive messages from the energy meter through the PLC network. PLC here stands for power line communications. That means the protocols used for communication and networking over the energy cables. With this protocol, we have near real-time access to energy data. And as you can imagine, these devices enable a lot of different use cases. We have instant availability of our energy meters, but also access to alerting and monitoring messages. And these, for example, could be used also in IoT and home automation systems. But we are interested in NILM, so let's see what kind of data is received from this device. You can see the Chain 2 device. This is a plug device. Basically, we are receiving three kind of messages from the energy meter. The first one are alerting and monitoring messages. That means that you could receive a message every time a service outage is near, or you can receive a message about your daily consumption or monthly consumption. So this kind of messages for monitoring and alerting. But we are interested in the other two messages that are quarter-hour frames and event-based frames. For quarter hour, we mean that we are going to receive a sample taken every 15 minutes. So as you can see from this plot, you can see the green square that we have a sample with the instantaneous power every 15 minutes. And then we could have also event-based frames. That means that we are going to receive a message each time an event is triggered. And these events consists in crossing thresholds. Indeed, we have thresholds, as you can see. Here we have thresholds with a range of 300 watts. And each time a threshold is crossed, you will receive a message. As a result, the data collected will be irregular. So we have an irregular sampling pattern. And this is different from the papers from studies in scientific literature and NILM methods in research studies. Indeed, this kind of papers study devices such this one, that is a clamp-based device, a traditional IoT device used in NILM. This device is provided with a probe that will sense the energy in your meter. So it is not receiving messages from your meter, but it has a probe to sense the power. Usually, this kind of devices work with a fixed sampling rate. For example, 1 second. That means 1 sample for second, 1 hertz. And as a result, this will generate a higher volume of data, and we can see a comparison here. We have the blue signal, that is a clamp-based high-resolution signal, and then the orange one, that is a low-resolution chain-tune-based signal. And you can see the orange one is a good approximation of the clamp-based, and also we have less messages. Indeed, in the first case, we have 86,000 messages in a day, while in the second case, we have just 2,000 messages. That means that we will ingest fewer, lower traffic, and we are processing less data. And this means that we are saving costs. Okay, but let's see algorithms used in this field. We can categorize algorithms in different ways. We could have supervised or unsupervised techniques. Also, NILM can be modeled as a classification problem or a signal reconstruction. Indeed, in classification problem, we want to classify on and off states of appliances. So basically, we have multi-label classification for each timestamp of interest. While in signal reconstruction, we want to extract the signal. So basically, we want to isolate the signal from each appliance. Several algorithms have been developed over time. The first one was combinatorial optimization, and it is a mathematical optimization to solve an optimization problem for each period of interest, with the final goal of minimizing an estimation error. You could have also more advanced mathematical models, such as factorial hidden Markov models. That means that you are modeling an ILM as transitions between different states. Most recent techniques actually are based on machine learning approaches, as you can imagine. So we have traditional machine learning here. I mean that we have handcrafted the feature extraction, so feature extracted from the time series. And then we could use traditional algorithms such as XGBoost or even linear models. But actually, the most effective models today are deep learning based. We have convolutional neural networks and recurrent neural networks used. And the first attempt to apply these networks to this field was done by Jay Kelly in this paper, Deep Neural Networks, Neural NILM. Jay Kelly is also the author of this open source toolkit on GitHub that implements all of these algorithms, but also define standard interfaces for datasets and also metrics for benchmarking. Okay, but the main limitation of these techniques is that they rely on regular sampled data, which we have seen are different from real chain-to data that we receive from our energy meter. So we started investigating studies on these, but the only attempt to apply an ILM to chain-to data has been done by Manca, that is an Italian researcher, so by an Italian group. As you can imagine, this is an Italian standard. And this study, again, modeled an ILM as a multi-label classifier. So here we have an input, a signal over the time. You want to solve for each timestamp a binary classification for each appliance. So we have multi-label. And they used a deep neural network autoencoder. This is the architecture, is based on convolutional, but it's not important. What is important is that this network works with a sampling rate of 1 minute. That means that the input data has a sampling rate of 1 minute. And this network is trained on public available clamp-based data. So again, we are studying chain-to data, but the authors trained this network on public-based, on clamp-based signals. And they want just to verify the performance degradation in applying this network that is trained on clamp-based data to chain-to data. But in order to apply these to chain-to data, they implemented an aggregation logic in order to get, with the final goal, to get a signal with a 1 minute sampling rate from the chain-to data. They basically, you can imagine as the chain-to signals that we have seen with quarter messages and event crossing. The signal, each sample is retained at its level from sample to sample, and then these will be downsampled at 1 minute. Okay, that's fine. So it's a work about chain-to data. But there is a huge problem in this paper because it has a limitation. Indeed, they for their experiment they used simulated chain-to data, but actually they messed up the simulation of the chain-to data. Indeed, in order to obtain a chain-to data, we want to apply a chain-to filter, so taking a sample every 15 minutes and then this logic to extract event crossing. but actually they apply this logic after the subsampling step used to match the network input. So the simulation is messed up, and so it's a huge limitation for this good paper. And we fixed this simulation by filtering the signal before the subsampling, and we did experimentation on a public dataset. I'm going fast because I haven't enough time, but we have a public dataset, UKDale, and the most popular datasets are UKDale and Refit. We have 18 houses with 2 years of data at 1 second resolution. And we did experiments on these public datasets, and we measured the approach by the authors, and then our approach consisted in training and testing the network on simulated chain-2 data. Indeed, they trained this network on clamp-based simulated data, simulation on clamp-based data. But we think that training on these chain-2 data will enhance and will help the network to adapt to the pattern of chain-2 data. And this is confirmed with the final metrics. But I think I finished my time. So to wrap up, we have covered a lot of topics today, and I apologize if it was too quick. But I hope that the key ideas were clear, and that this presentation has provided useful insights on NILM approaches. And I'm available for questions also offline, so feel free to reach me out for questions.
Thank you for that awesome talk. We do have one question in the Q&A, and I will bring that up on stage for you. Are you able to see that?
Yeah, I can see. What is the size of your evaluation set? So yeah, sorry, I was really fast in this in this part. So basically, we have 18 houses in the public dataset with 2 years of data, and we used the 15 houses for training and validation with a temporal split for training and validation. I think 80-20, but with a temporal split. And then we used 3 completely new houses for testing with the same period, but 3 new houses. Okay, I can see another question. Thank you for the presentation. How is the time series treated as the input of the CNN? Is it like a 1D sliding window? Okay, this is a good question. And actually, the network has input a chunk of 8 hours. So I think 480 samples. Each sample is 1 minute, and it has also some windowing. So we include at the beginning and the end of the signal a window. So we divide the original time series in chunks, but we have overlapping regions between chunk to chunk. And these allow us to build the output signal.
Fantastic. And that brings us right up to our time. Thank you so much for speaking today. We did a little switch on you with hosting. You had to go open another session, so I just wanted to close out. But thank you so much for being a part of PyData Global. Attendees, thank you so much. If you'd like to ask any more questions or continue the conversation, hop on over to our Discord channel where you can absolutely just continue chatting about that. And this session, as soon as we end it, will be available for rewatch. So again, thank you so much for speaking today and being a part of PyData Global.
Thank you for joining.